Imagine this. Your most secure digital device, maybe your smartphone or the smart home hub running your security, maybe even a critical sensor deep inside a factory, suddenly has its deepest secrets, its encryption keys, just stolen.
Right.
And here's the really weird part. It's not through some, fancy software hack, no malware, no phishing scam.
Mm-hmm.
It's simply by listening to its faint hum or watching these tiny, almost invisible fluctuations in its power draw.
Yeah.
Sounds like something out of a sci-fi movie, doesn't it? But this isn't fiction. It's a very real and actually growing threat.
It really is.
So today we're going to take a deep dive into this fascinating and, frankly, a little bit unsettling world of side channel analysis attacks. SCA for short.
That's right.
These aren't your typical digital breaches, the ones exploiting bugs in the code. No, these are about exploiting the subtle physical side effects of computing itself.
The physics of it.
Exactly. We'll explore how incredibly advanced techniques, including things like deep learning, even modified 3D printers, are making these attacks way more powerful and easier to pull off than ever before.
It's evolving fast.
But it's not all bad news. We'll also uncover a pretty revolutionary new defense that could help secure our increasingly connected world from these, sneaky threats.
Yeah, there's definitely hope on the horizon.
Our mission today really is to give you a shortcut to getting properly informed about this critical but often kind of overlooked aspect of cybersecurity.
It doesn't get the headlines like software breaches, but it's fundamental.
Absolutely. So we'll unpack the core problem, reveal the surprising sophistication of these modern attacks, and then shine a light on a breakthrough in countermeasures that seems to offer genuinely robust protection, crucially without the massive downsides of older methods.
And for this, we're drawing our insights today from some really groundbreaking research. Our discussion is mainly inspired by a key article called Electromagnetic and Power Side Channel Analysis: Advanced Attacks and Low Overhead Generic Countermeasures Through White Box Approach.
Quite a title.
It is, yeah, by Debayan Das and Shreyas Sen. This paper really digs into the fundamental causes of these hardware vulnerabilities, and importantly, it maps out a really promising path forward for securing our digital hardware, like right from the silicon level up.
Okay, sounds like we've got some solid ground to cover. Let's start with the basics then. So let's unpack this idea, side channel attacks. We all kind of get that modern crypto algorithms, AES and the like, they're designed to be mathematically incredibly secure.
Rock solid, mathematically speaking.
Right. With the key lengths we use today, trying to crack them with brute force is it's basically impossible. It would take, longer than the age of the universe?
Something like that, yeah. Computationally infeasible.
But what happens when these mathematically sound algorithms are actually put onto a physical device, running on real silicon in the, real world?
And that's where the story gets really interesting. What's fundamentally going on here is that the physical implementation itself becomes the vulnerability, not a flaw in the math, but how the math is done.
Okay.
So when a crypto algorithm runs on an embedded chip, whether it's encrypting data, generating a key, whatever it performs operations, and these operations, just by their nature, interact with the physical world.
They have to use power, right?
Exactly. They use power, they cause tiny voltage drops, they generate heat, they emit faint electromagnetic fields. These interactions aren't perfectly clean or isolated. They actually leak information.
Leak information? How?
Well, we're talking about tiny but correlated bits of data. They show up in different physical forms. Tiny fluctuations in the chip's power consumption profile over time. The specific pattern of electromagnetic EM emissions it radiates. Subtle variations in the timing of its operations. Maybe one calculation takes a few nanoseconds longer depending on the data.
Wow.
Or even in more abstract ways like patterns of cache hits and misses in the processor's memory. An attacker can essentially listen to these subtle side channels to figure out the secret key, completely bypassing the mathematical strength of the encryption itself.
That's a really vivid picture. It's almost like a spy trying to figure out a secret message, not by actually cracking the code, but by watching the person sending it very closely.
Yeah.
Noticing, their unique posture, maybe their breathing patterns, the specific way their pen moves across the paper, those subtle, unintentional tells that reveal what's actually happening underneath.
That's a perfect analogy. It's looking around the code, not at the code.
Yeah.
It's this indirect, almost forensic way of getting the secret key. And as we'll see, because it sidesteps the mathematical complexity, it's often far, far more efficient and practical than trying to guess a key through brute force. which, as you said, is just totally unfeasible for strong modern ciphers.
It makes sense when you put it like that. Scary, but it makes sense. Hashtag YSCA is a critical problem for connected devices. Now, someone listening might be thinking, okay, a tiny power fluctuation, a faint EM hum from some little chip, how big a deal can that really be?
Yeah, it sounds almost negligible.
Right. But if we connect this to the bigger picture, I mean, just the sheer number of internet-connected devices flooding into our lives, everything from smart speakers and thermostats in our homes,
To industrial sensors monitoring critical infrastructure, power grids, factories.
even medical devices, implanted or wearable. It means that even the weakest link in this huge interconnected network can become a massive point of vulnerability.
Absolutely. It's not just about securing one device in isolation anymore. It's about the trustworthiness and the resilience of these entire systems that we increasingly rely on for, well, everything.
Modern society runs on this stuff now.
It does. And this brings us to a really crucial question. Who is most at risk here? The paper specifically highlights that resource-constrained, small form factor edge devices, which are incredibly common in the Internet of Things, the IoT, they are particularly vulnerable.
Why them specifically?
Well, think about how they're designed. They're optimized for low cost, minimal power consumption, tiny physical size.
Right, like sensors, smart plugs, things like that.
Exactly. And that often means they lack the robust physical shielding, the sophisticated built-in security features, or even just the computational overhead that larger, more powerful systems like servers or laptops might have. Their very design, which is honed for efficiency and cost, kind of inadvertently makes them prime targets for side-channel attacks.
So their strength becomes a weakness in this context.
In a way, yes. And we are definitely not talking about purely theoretical threats here, stuff just cooked up in a lab. The article gives some genuinely chilling, real-world examples that really hammer home how pervasive and dangerous these attacks are, like right now.
Okay, lay 'em on us.
All right, first, consider remote power SCA. This has been successfully used on multi-tenant FPGAs.
Okay, FPGAs are those programmable chips, right? What's multi-tenant?
Right. FPGAs are field-programmable gate arrays chips you can reconfigure. Multi-tenant means different users or applications might be sharing resources on the same physical chip. Think cloud computing, but at the hardware level.
Ah, I see.
So an attacker running their own code on one part of the FPGA could potentially, stealthily, monitor the power usage of another part of the chip, effectively spying on its neighbor's crypto operations to steal keys. That's like an insider threat built right into the silicon.
Wow, okay, that's devious. What else?
Then there's far-field EM SCA. This one is really eye-opening. Attacks have been demonstrated from as far as 10 meters away.
10 meters? Seriously?
Seriously.
Mhm.
On an ARM Embed TLS implementation. Now, Embed TLS is a really common, lightweight security library designed specifically for embedded devices, perfect for IoT.
So you're saying someone could be sitting across the street, basically?
Potentially, yes. Extracting your encryption keys just by listening to the faint electromagnetic waves coming off your smart device. It's like this silent, invisible radio broadcast of your deepest secrets.
That is deeply unsettling.
It is. And we've also seen very concrete compromises in everyday tech. Think about smart lighting systems. The paper mentions how Philips Hue, the popular smart light bulbs,
Yeah, I have those.
they were hacked by exploiting power side channels on the Atmel microcontrollers inside them. This shows how even devices we think of as pretty innocuous, low risk, can actually be deeply compromised through these physical means.
Right, not just high security stuff.
Not at all. And perhaps most alarmingly, while it wasn't a direct SCA exploit itself, the paper brings up massive DDoS attacks, like the infamous DNS attack a few years back.
Oh yeah, that took down half the internet.
Exactly. It leveraged millions of compromised internet-connected webcams. And while the initial compromise might have been different, it powerfully shows the catastrophic potential when huge numbers of vulnerable IoT devices are taken over. The paper makes a strong case that if these devices can be controlled by sophisticated attackers, then techniques like SCA could absolutely be used as part of the toolkit to gain that control, leading to similar large-scale threats. It really emphasizes why we need protection at every single layer, especially the hardware.
So these aren't just edge cases.
Not at all. They're a clear and present danger, and it scales up massively with every new billion IoT devices we connect. And here's a critical detail that really drives home the severity, something that often surprises people. The attack complexity reduction.
Okay.
Mathematically, breaking AES 256 with brute force needs something like 2,256 attempts, an absurdly huge number, practically infinite.
Right.
However, using EM or power side channel analysis, that monumental task can potentially be reduced to just 213 attempts.
Wait, 2 to the power of 13? That's tiny in comparison.
Well, it's a staggering difference. It turns an impossible task into something that's often practically feasible, sometimes doable within minutes or hours in a lab, with the right equipment.
Wow.
And what's even more revealing is that just moving from, say, AES 128 to the stronger AES 256, which seems like a big security upgrade.
Yeah, you'd think that would help a lot.
Against side-channel attacks, it only roughly doubles the resilience. It doesn't give you that exponential jump in protection you get against mathematical brute force.
So just using a stronger algorithm isn't enough.
Exactly. It shows that simply relying on stronger math doesn't automatically make devices safe from these kinds of physical attacks.
Yeah.
We desperately need a different, more fundamental approach to securing the hardware itself.
That is quite a wake-up call. Okay, so let's dig into how these attacks actually work. You mentioned different types. Let's start with the more traditional methods and see how they've evolved. Initially, you had these non-profiled attacks.
Right. Non-profile attacks are sort of the classic approach. In essence, an attacker collects these traces, those precise measurements over time of power use or EM emissions, while the crypto chip is doing its thing.
Okay, they're recording the chip's activity.
Exactly. Now, to make sense of these traces, the attacker usually needs either the known plaintext, the original data before encryption, or, more commonly in the real world, the known ciphertext, the encrypted data, because ciphertext is often publicly transmitted or stored.
Right, you can often grab the encrypted stuff.
Precisely. So with these traces and some known data, plaintext or ciphertext, the attacker then uses statistical models. These models are often based on something called a device's Hamming weight.
Hamming weight.
Yeah, it's simply the number of ones in a binary representation of a piece of data like a key byte. Or sometimes they use Hamming distance, HD, which is the number of bits that differ between two binary numbers. The idea is that processing data with more ones might consume slightly more power, or processing data that changes a lot might cause a bigger power spike.
Ah, okay, so they're looking for statistical links between the data and the physical signals.
Exactly. They try to correlate these statistical models, like predicted power consumption based on hypothetical key bytes, with the actual collected physical traces.
And this is usually done, what, byte by byte for something like AES?
Typically, yes. For algorithms like AES that work on bytes, you attack it one byte of the key at a time. The paper details this process under names like correlational power analysis, CPA, or correlational EM analysis, CEMA.
So you just keep analyzing traces, trying different key byte guesses?
Right. You hypothesize a key byte, predict the power trace based on that hypothesis using your Hamming weight or Hamming distance model, and then see how well that prediction correlates with the real traces you collected. You do this for all 256 possible values of the byte.
And the correct one will eventually stand out.
Exactly. The correct key byte's predicted signature will show the strongest correlation with the actual measurements, eventually emerging from the background noise as you analyze more and more traces. It's like tuning a radio dial very carefully until the station comes in clearly. Hashtag, the rise of profiled SCA attacks in machine learning.
Okay, that makes sense for the traditional methods. But then things got really interesting, right? Machine learning enters the picture.
Oh, yeah. This is where the game truly changes. Just like in so many other fields, applying machine learning has supercharged these attacks, made them significantly more potent, more efficient. Profiled attacks are generally orders of magnitude more powerful than non-profiled ones, and crucially, they often require far, far fewer traces to succeed.
How do they work differently? What's profiling?
Right. Profiled attacks operate in two distinct phases. First, there's a training or profiling phase. Here, the attacker needs to get their hands on an identical device to the target, one they have complete control over.
Okay, like buying the same model of smart plug off the shelf.
Exactly. On this control device, they run a massive number of cryptographic operations, maybe using known keys, and carefully measure the side channel leakage for each operation. They build up a huge data set.
And then they train an AI on this data.
Precisely. A machine learning model is trained on this extensive data set. Its job is to learn the intricate, unique leakage patterns associated with different key bytes, or maybe intermediate values calculated inside the crypto algorithm. It builds a highly detailed profile or template of how that specific device model leaks information.
Okay, so they build a master profile. Then what?
Then comes the attack phase. This pre-built, highly refined template is used to break a different target device, one that's similar but previously unseen by the model. And here's the kicker. In some cases, especially with deep learning, this attack phase can succeed with as little as a single trace from the target device.
One trace. That's incredible.
It dramatically reduces the effort, the time, and the amount of observation needed for a successful attack. It basically turns what was a statistical guessing game into a much more precise pattern recognition problem.
The paper traces this evolution pretty well, right? From early Gaussian template attacks back in 2002
Yeah, those were some of the first profiled methods.
to the rise of machine learning SCA around 2011. And since then, it's just exploded using techniques like support vector machines, SVMs, random forests, RF.
And increasingly, deep neural networks, DNNs, which are the powerhouses behind a lot of modern AI. Each new ML technique tends to make the attacks faster, more robust against noise, and just generally more effective, even when the leakage signal is really faint or messy.
But even with machine learning, there was this major hurdle, wasn't there? This issue of device variability.
Absolutely. That was a big bottleneck for a while.
You could train a model on one specific chip, but it often wouldn't work very well on another chip, even if it was supposedly identical right off the same production line.
Exactly. Tiny manufacturing differences between chips, slight variations in operating voltage, even temperature fluctuations, they could all subtly change the leakage profile just enough to throw off a model trained on only one device.
Which led to the development of XDeep SCA, the cross-device deep learning side-channel attack.
That's right. XDeep SCA tackled this head-on. And the core challenge it addresses is really fascinating when you think about it. The variations between supposedly identical devices for the same key byte are often significantly larger than the variations between different key bytes on the same device.
Wait, say that again? Variations between devices are bigger than variations between keys on one device.
Often, yes. It makes building a portable attack model really tricky. It's like trying to identify someone reliably just by their fingerprint. If their fingerprint changed slightly every single day, the day-to-day variation might be bigger than the difference between their fingerprint and someone else's on any given day.
So the model would basically overfit to the specific training device. It learns its unique quirks rather than the general pattern.
Precisely. It becomes too specialized. It learns the noise profile and specific characteristics of the training device, rather than the fundamental underlying cryptographic leakage pattern that's common across all devices of that type. XDeep SCA overcomes this by introducing multi-device training.
Ah, so instead of training on just one device.
They train the deep neural network using traces collected from multiple different devices of the same type. This diverse training data forces the model to ignore the device-specific noise and variations and instead learn the more general, common leakage features. It learns to generalize much better.
Makes sense. Teach it what's common, not what's unique to one sample.
Exactly. It makes the resulting attack model much more robust, adaptable, and portable across different physical chips, even those with subtle manufacturing differences.
And the results they got with XDeep SCA, according to the paper, were pretty incredible.
They really were. They achieved over 99.9% accuracy for single-trace attacks on unseen devices.
Single trace again.
Yeah. Meaning an attacker armed with a well-trained XDeep SCA model could potentially grab a key from a target device with just one recorded side-channel trace. That's a huge threat.
And it also lowered the number of traces needed overall, right? The MTD.
Right. It demonstrated a 10x lower minimum traces to disclosure, MTD, compared to traditional CPA. For an attacker, needing 10 times fewer observations to crack the key is a massive advantage. It dramatically lowers the bar for launching an effective attack. It means more embedded devices become vulnerable, even if the attacker can only capture a handful of leakage traces. It was a significant leap forward for the attackers.
Okay, so the attacks are getting smarter, faster, needing fewer traces thanks to things like XDeep SCA. But there's still the physical problem. How do attackers even find where on the chip the most useful leakage is actually happening? You can't just probe anywhere, can you?
That's a great point. Finding that sweet spot on the chip surface, the exact location that emits the clearest, most information-rich side-channel signal, was traditionally a really manual, painstaking, and incredibly time-consuming process.
Like trying to find the best spot to put a microphone in a noisy room.
Exactly. Or maybe like trying to find a tiny radio transmitter hidden somewhere on a circuit board just by listening. It involved manually moving a probe micron by micron, taking measurements, analyzing.
Yeah.
It can take days or weeks. This sounds like an area just begging for automation.
You'd think so.
And you'd be absolutely right. This brings us to the question, how can attackers make the physical part of the attack more efficient too? The answer presented in the research is SCNIFR,
SC-NIFR.
Yeah, it's described as a low-cost, automated, end-to-end EMSCA attack framework. And its approach is really quite clever and maybe a bit surprising. It uses a standard 3D printer.
A 3D printer, like the ones people use for making plastic models.
Exactly. Modified, of course, to hold a sensitive electromagnetic probe instead of a plastic extruder. The 3D printer's precise movement capabilities are repurposed to accurately and systematically scan the probe across the chip's surface. It essentially automates that incredibly tedious process of finding the best leakage points.
Okay, that's definitely one of those surprising facts. Using a hobbyist tool for advanced hardware hacking. How does it find the leakage spots efficiently, though? Does it still have to check every single point?
No, and that's the clever part. SC-NIFR uses what's called a greedy gradient search heuristic. It's an intelligent optimization strategy. Instead of exhaustively scanning every point on the chip, which for an n-by-n grid would take n-squared measurements, incredibly slow, it intelligently moves towards areas of stronger leakage.
How does it know where the stronger leakage is?
It uses metrics like test vector leakage assessment, TVLA, or signal-to-noise ratio, SNR, at each point it probes. TQLA is a statistical test to see if there is any data-dependent leakage occurring, while SNR measures how strong that leakage signal is compared to the background noise. SC-NIFR uses these metrics like a guide. It figures out which direction shows increasing leakage, and moves the probe that way.
So it follows the signal like a heat-seeking missile.
That's a good way to put it. It continuously converges on the points of highest EM leakage. This intelligent search takes only roughly ON iterations proportional to the width of the chip, not the area compared to the much, much slower n-squared for an exhaustive search. It dramatically speeds up the initial reconnaissance phase of the attack.
So what does this mean in practical terms? How much faster does this make the whole attack process for an adversary?
It cuts down the SEMA attack time significantly, the paper mentions, by a factor of n compared to exhaustive search, and over 20 times faster than just randomly picking spots to probe. But the most striking statistic, the one that really highlights its impact, is this. In terms of the number of traces needed for a complete end-to-end attack, including finding the spot and extracting the key, SC-NIFR offers potentially a 100x reduction compared to using exhaustive search methods.
100 times fewer traces needed overall.
Yes, that's a potential game changer for attackers. It makes electromagnetic side-channel attacks much more practical, faster, and worryingly accessible to a broader range of adversaries, not just nation-states with huge labs. It effectively lowers the technical skill and resource bar needed to mount these sophisticated physical attacks.
Okay, so the attacks are getting incredibly sophisticated. We've got traditional SEPA-SEMA, then AI-boosted profiled attacks like XDeep SCA needing just one trace, and now automated physical scanning with SC-NIFR making the whole process faster and easier. It really paints a picture of relentless ingenuity on the attacker side.
It definitely does. The threat landscape is constantly evolving.
So what have engineers and security researchers been doing to fight back? How do you protect these vulnerable embedded devices from these invisible threats?
The paper groups the traditional defenses into a few categories, right? Logical, architectural, and physical or circuit level.
That's right. And regardless of the category, the fundamental goal behind almost all effective countermeasures is the same. You want to decrease the signal-to-noise ratio, SNR, make the secret signal harder to hear.
Exactly. Think back to that analogy of hearing a whispered secret in a noisy room. The leakage is the whisper. The chip's normal operation is the background noise. Countermeasures try to either make the whisper much, much quieter, suppress the signal, or, more commonly, make the room incredibly loud, inject noise, drowning out the whisper so it's impossible to isolate.
Okay, so noise injection and signature suppression.
Those are the two main strategies, yes.
Let's quickly look at those first two categories you mentioned, logical and architectural countermeasures. What do they involve?
Okay, so logical countermeasures often involve power balancing techniques, things like wave dynamic differential logic, WGDL, or dual rail precharge DRP circuits. The basic idea here is to design the digital logic gates in such a way that they theoretically consume the same amount of power regardless of whether their processing is 0 or a 1.
Trying to create a perfectly flat power profile.
Exactly. If the power consumption doesn't fluctuate based on the secret data being processed, then there's no differential signal for a CPA attacker to latch onto.
Makes sense. And architectural ones.
Architectural countermeasures work at a slightly higher level. They introduce distortions, either in the amplitude of the signal or, more often, in the time domain, to try and confuse the attacker.
How do they do that?
Think about techniques like inserting random dummy operations calculations that don't actually contribute to the crypto result but still consume power and time, or shuffling the order of operations unpredictably, or even techniques like randomly skipping clock cycles. The goal is to make the timing and power profile of the real cryptographic operations completely unpredictable and unlinkable to the secret data. It's obfuscation through randomness and timing jitter. Hashtag tag tag limitations of existing approaches.
Okay, those sound like clever ideas in principle, but the paper suggests they have some significant drawbacks, right?
They do. While these traditional methods represent genuine efforts to improve security, they often come with pretty hefty trade-offs that really limit how practical they are, especially for widespread use, and sometimes limit their long-term effectiveness too.
Like what kind of trade-offs?
Well, for starters, logical and architectural countermeasures are typically highly design-specific and algorithm-specific.
Meaning they only work for one particular chip design or one specific crypto algorithm?
Pretty much, yeah.
Yeah.
A WDDL implementation for AES won't just work for, say, an ECC implementation. You have to redesign it. This means they can't be easily applied across different crypto cores or reused for different cryptographic tasks without significant, costly re-engineering for each new design. This lack of flexibility is a major hurdle for the industry, which really needs more generic plug-and-play solutions.
And they also have big overheads, don't they, in terms of chip size, power?
Huge overheads, often. The paper specifically mentions WDDL, which sounds good on paper, but can incur something like a 3x area overhead on the chip, meaning the chip needs to be 3 times bigger.
Wow.
Plus a 4x power overhead. Think about that for a battery-powered IoT device. 4 times the power consumption is often a total non-starter. And it can also cause a 4x performance degradation, making everything run slower.
Okay, those are massive penalties.
They are. Similarly, architectural masking techniques, like adding lots of dummy operations, can easily lead to more than 2x area and power overheads.
Right.
These are really significant costs, especially for those resource-constrained IoT devices we keep talking about, where every milliwatt of power and every square millimeter of silicon drastically impacts the final cost, the battery life, and the overall feasibility of the product.
So these solutions often just aren't practical for many applications.
Exactly. High area, power, and throughput overheads are really common limitations. And furthermore, the paper points out a critical vulnerability. Even some of those clever time distortion techniques, like clock skipping or random delays, have actually been shown to be defeated by advanced attacks. Specifically, attacks using convolutional neural networks, CNNs, a type of deep learning model good at analyzing time series data.
So the AI can see through the timing obfuscation.
In some cases, yes. The AI can learn to compensate for the introduced jitter and still extract the underlying signal. It shows that even smart obfuscation isn't always foolproof against intelligent adversaries.
Okay, so logical and architectural have issues. What about the third category? Circuit-level physical countermeasures.
Right. These initially sound a bit more promising because they often aim to be more generic, less tied to the specific algorithm. They involve things like actively injecting noise into the power supply to mask the signal, or using supply isolation circuits. These often employ components like integrated voltage regulators, IVRs, or series low dropout regulators, LDOs, to try and clean up the power supply reaching the crypto core, filtering out those revealing fluctuations.
Trying to build a wall around the crypto engine's power supply?
Kind of, yeah. But even these more generic physical solutions run into their own challenges. They can suffer from meeting large passive components like inductors or big on-chip capacitors, which again, eat up valuable chip area and increase cost.
Okay.
And here's a critical, almost ironic insight the paper highlights. Those very on-chip capacitors, the ones intended to filter noise and stabilize the voltage, they can themselves become leakage sources. Information can leak out through the higher metal layers above these capacitors on the chip. So the countermeasure itself inadvertently creates a new, unintended side channel.
Wow, that's counterproductive.
It really is. Plus, things like series LDOs, which are designed to provide a stable voltage, inherently work by instantly tracking and reacting to the current draw of the circuit they're supplying. In doing so, they can actually end up transmitting that very data-dependent current signature onto the main power rail they're supposed to be isolating it from.
So they leak the information they're trying to hide.
Effectively, yes, by their very operation. It really feels like a constant game of whack-a-mole with many of these traditional approaches. You fix one leak, another one pops up somewhere else. Hashtag tag tag the need for a white box understanding.
Okay, so it seems like a lot of the traditional defenses either fall short in terms of security, they're too specific to one design, or they come with these really heavy penalties, performance, power area that make them impractical.
That summarizes the challenge pretty well.
Which really brings us to a crucial question. If we want truly effective countermeasures, ones that are low overhead, broadly applicable across different designs, generic, and can actually stand up to these sophisticated AI-powered attacks, what's been missing? What's the secret ingredient we need?
The crucial missing piece, and this is really the core argument of the paper we're discussing, is a white box understanding of the problem.
White box versus black box.
Exactly. Most of the existing circuit-level solutions we just talked about tend to treat the crypto engine and its leakage mechanisms as a black box. They try to apply external bandages like filters or noise injectors without necessarily having a deep, fundamental understanding of why and how the leakage is happening inside that box.
They're treating the symptoms, not the cause.
That's a great way to put it. The research argues compellingly that we need to shift our perspective. We need to analyze the crypto integrated circuit, the crypto IC, from the ground up with a complete, transparent, white box view of its internal workings, its physical layout, the materials used, everything. We need to meticulously root cause the precise origin of the electromagnetic and power supply leakage.
Get right down to the fundamental physics of it.
Precisely. Because you simply can't design a truly effective, efficient defense against something until you understand exactly why and how it's leaking information, right down to the most microscopic physical interactions happening within the chip's structure. This shift in perspective, from treating it as an unknown black box to understanding it as a transparent white box, is what unlocks the potential for a genuinely revolutionary defense.
Okay, this is where it gets really interesting. The researchers took this white box approach, digging deep into the chip's guts. What did this deep analysis actually reveal about the true fundamental source of that EM leakage? Was it the transistors themselves, the active switching components? That seems like the obvious culprit.
You'd think so, wouldn't you? But what's truly fascinating here, and actually quite counterintuitive, is that the analysis showed it's not the transistors directly generating the most significant, easily detectable EM leakage.
Really? Then what is it?
Instead, the primary culprits turn out to be metal layers and vias the microscopic wiring that carry the electrical current throughout the chip.
The interconnects.
Exactly. As the digital gates in the crypto core switch on and off, doing their computations, they create rapidly changing electrical currents. It's the flow of these switching currents through the intricate stack of metal layers and the vertical connections, vias between them, that generates the electromagnetic radiation attackers can pick up.
Okay, so the wiring acts like tiny antennas.
Precisely. And here's the kicker, the really surprising fact the paper highlights, based on their analysis and simulations. The higher metal layers on the chip are generally thicker and physically larger.
Right, the top layers of wiring.
And because of their dimensions, they act as much more efficient antennas at the typical operating frequencies of these crypto cores. So EM leakage radiating from these top layers, the ones closest to the surface of the chip, like metal 9 and above and the Intel 32 nanometer process they simulated, has a significantly higher probability of escaping the chip and being detected by the commercial EM probes attackers use.
So it's like having your most sensitive conversations happening right next to big open windows on the top floor of a building, making it super easy for someone outside with binoculars or an EM probe to spy on you.
That's a perfect analogy. It's a fundamental physical insight derived directly from that white box analysis.
Right.
And it completely changes how you think about defending against EM leakage.
Okay, so if the higher, thicker metal layers are the problem, acting like efficient antennas, the core insight for defense seems almost obvious in hindsight. Don't let the sensitive cryptocurrent flow through those leaky top metal layers.
Exactly. Keep the sensitive signals away from the efficient radiators. This brilliant realization, stemming directly from that white box understanding, led the researchers to develop Stellar.
Stellar, what does that stand for?
It stands for Signature Attenuation Embedded Crypto with Low-Level Metal Routing.
Okay, low-level metal routing. That sounds like the key part.
It is. Stellar's core idea is both elegant in its simplicity and potentially profound in its impact. It proposes to route the entire crypto core, all its sensitive internal wiring, exclusively within the lower, thinner metal layers of the chip.
Down in the chip's basement, basically.
Exactly. These lower metal layers, being thinner and smaller, are inherently much less efficient at radiating EM signals at the frequencies of interest. Their antenna capability is significantly reduced.
Okay, so you confine the sensitive signals to the less leaky layers. Is that all?
Not quite. Then, this carefully routed crypto core is embedded within a specialized piece of hardware called the signature attenuation hardware, or SAH. This SAH acts as a local shield or filter, and its job is to further suppress the critical data-dependent signature before any residual current can even reach the higher, more leaky metal layers that eventually connect to the external power pins of the chip.
So it's a two-pronged approach. Route locally in quiet layers, and then add an extra layer of suppression before connecting to the outside world.
Precisely. It's like having those secret conversations not just in the basement, but in a specially soundproofed, shielded room within the basement, completely isolating them from any potential listening posts on the upper floors or outside. This local confinement and active suppression right at the source, deep within the chip, is crucial for stopping the leakage before it even starts.
And this stellar routing strategy, this clever layout approach, works hand in hand with the actual signature attenuation hardware itself, which they call CDSA.
That's right. Current Domain Signature Attenuation, CDSA hardware. This CDSA unit is really the heart of the defense mechanism, the culmination of years of research building on earlier concepts, and it brings together all these white box insights into a truly robust and, as we'll see, efficient defense.
So what's the main goal of CDSA? How does it attenuate the signature?
The fundamental goal of the CDSA hardware is to ensure that the current drawn by the crypto engine from the main external power supply is effectively constant, completely independent of the variable, data-dependent current fluctuations happening inside the crypto core itself as it processes secret data.
Decoupling the internal activity from the external power draw.
Exactly. By perfectly decoupling these two current flows, it prevents any information about the secret key from being imprinted onto the power supply signature, which is precisely what CPA attackers are looking for. It's about feeding the crypto engine the average power it needs, but doing so in a way that reveals absolutely nothing about what specific computations it's performing at any given microsecond.
Okay, this sounds almost like magic. How does it actually achieve this? Providing a perfectly stable current to a device that, by its very nature, is drawing a rapidly fluctuating current internally. The engineering must be pretty clever.
It is quite clever, involving several key components working together seamlessly. It starts with a high-impedance cascode current source CS stage. This is designed to provide a very stable average current to the crypto core. The cascode design basically makes the output current highly resistant to any voltage fluctuations happening within the crypto core, keeping it steady.
Okay, so it provides the baseline power.
Right. Then there's a low bandwidth switched mode control, SMC loop. This loop slowly adjusts the average current supplied by the CS stage to match the crypto core's overall long-term average power consumption. But, and this is absolutely critical because it's low bandwidth, it doesn't react instantly to those fast data-dependent current spikes and dips that carry the secret information.
So it smooths out the demand signal.
It ignores the fast fluctuations. Now, what happens to those fluctuations? Any momentary excess current needed by the crypto core, above the stable average being supplied, or any momentary decrease in demand, the very key-dependent signature we want to hide, is immediately and silently handled locally. It's shunted away through a special biased PMOS transistor, acting as a bleed path.
A bleed path, like a pressure release valve.
Sort of, yeah. This bleed path acts as an inherent ultra-fast local negative feedback loop. If the crypto core suddenly needs less current, the excess from the stable supply is bled off. If it suddenly needs slightly more, the bleed path reduces its current draw to compensate. This ensures the total current drawn from the main supply remains constant, while the fast, information-rich fluctuations are entirely contained and managed locally within the CDSA unit.
It's like a local buffer or shock absorber for the current signature.
That's a great way to think about it. It provides a beautifully engineered system of supply and demand for current, where any excess information, any revealing fluctuation, is immediately consumed or compensated for internally, never making it out to the observable power supply pins.
And if this is done right, by bleeding off these tiny information-carrying fluctuations before they escape, could this provide what's called information-theoretic security, making the external leakage statistically indistinguishable from random noise?
It absolutely can, and that's the goal. The paper details the design principles. If the unit current provided by each slice of that cascode current source is meticulously designed to be higher than the maximum possible key-dependent variation in the crypto core's instantaneous current draw.
Then the bleed path always has enough range to absorb the fluctuations.
Exactly. If that condition holds, then the sensitive key information simply does not get transferred to the main supply current. It's essentially swallowed by the bleed path and dissipated locally as tiny amounts of heat, never reaching a point where it can be observed externally by an attacker measuring the power supply.
It's like dropping a pebble into a huge, fast-flowing river. The ripple just disappears instantly, unnoticed downstream.
That's a perfect analogy. It provides that critical level of security where the very act of observing the power supply yields no statistically meaningful information about the secret key. It fundamentally solves the leakage problem at its root, rather than just trying to mask it externally.
Okay, these ideas, stellar routing, CDSA hardware, they sound brilliant on paper, conceptually elegant, physically insightful, a real white box solution. But the real proof is always in the pudding, right? Did they actually build this? How did it perform when fabricated into a real chip?
They absolutely did. The true test is always in silicon. The researchers implemented a complete CDSA-protected AES-256 core in a TSMC 65-nanometer technology test chip. And crucially, they implemented it with the local lower metal routing strategy, keeping signals below metal 6 exactly as the stellar approach proposed. This wasn't just a simulation. It was a physical working proof of concept.
Okay, so they built the real deal. What were the results? Did it work?
The measurement results are genuinely impressive, and they really speak volumes about how effective this combined stellar and CDSA approach is. They measured an active signature attenuation of greater than 350 times for both power supply traces and electromagnetic emission traces.
350x attenuation, that sounds huge. How does that compare to the unprotected version?
It's night and day. For the standard unprotected AES implementation they also tested on the same chip, the power traces showed a clear, easily measurable signal swing of about 150 millivolts. You could practically see the encryption happening. Furthermore, in the EM traces for the unprotected core, the 14 distinct rounds of the AES algorithm were visibly discernible. It was like watching the algorithm run by looking at the EM field.
Wow, broadcasting its secrets.
Pretty much. But for the CDSA AES-2506 implementation, those same power and EM traces remain completely flat, entirely buried below the noise floor of their measurement equipment. This represents a truly massive suppression of the side-channel signal. It effectively rendered the cryptographic operations completely invisible to an attacker using standard power or EM measurement techniques.
It's like turning the volume of that whispered secret down so low that it's completely drowned out by the faintest background hum.
Exactly. It's truly silencing the leakage at the source. Hashtag unrivaled attack resistance.
That level of attenuation, that 350x signal suppression, is astounding from an engineering perspective. But what does it actually mean for an attacker? How much harder does it make their job of stealing the key?
The difference is stark. Let's put some numbers on it. The researchers found that the unprotected AES-256 core on their chip could be broken using side-channel analysis with a relatively small number of traces. Only about 8,000 traces for CPA, power analysis, and around 12,000 traces for CIMA, EM analysis.
Okay, that sounds achievable for a determined attacker.
Definitely feasible in a lab setting. But the protected CDSA AES-256 core, it remains secure even after they collected data from 1 billion encryptions.
1 billion, with a B, and still no key.
1 billion operations, and the key remains secure. They couldn't extract it using standard CPA or CIMA methods.
That's an incredible difference. The paper calls this an MTD improvement, right? Minimum traces to disclosure.
It's exactly. This represents an MTD improvement of at least 100 times compared to other existing state-of-the-art countermeasures that were evaluated under similar conditions. This isn't just an incremental step, it's a massive leap forward in practical security against these attacks.
A 100x improvement is huge, which immediately makes me ask the critical question. What about those really advanced AI attacks? Can things like XDeepSCA, the one specifically designed to pull signals out of noise, can they break this CDSA defense?
That's the million-dollar question, isn't it?
Yeah.
And this is where the paper's findings are truly groundbreaking and provide really robust answers. They specifically tested the CDSA protected core against those sophisticated DNN-based profiling power. SCA attacks the very kind designed to overcome noise and subtle variations.
Okay, the ultimate test. What happened?
For the standard unprotected AES core, a deep neural network could be fully trained with just 5,000 traces. Once trained, it achieved 99.9% accuracy and demonstrated it could craft the key with just a single trace from the target. Typical MLSCA vulnerability.
Right, but for the CDSA protected AES core.
The results were unequivocal. The DNN simply could not be trained. Even after feeding it 10 million power traces from the protected core, the AI model couldn't learn any meaningful correlation between the traces and the key bytes. It couldn't find a pattern. It couldn't converge.
10 million traces and the AI learned nothing.
Nothing useful for breaking the key. There was simply no discernible information left in the power signature for the AI to latch onto. This unequivocally demonstrates CDSA's effectiveness against even these advanced deep learning attacks. It essentially renders them useless because the foundation they rely on extracting patterns from leakage is removed. The leakage is gone.
So it seems to achieve that information theoretic security goal in practice, even against AI.
The evidence strongly suggests that, yes, it's a truly robust defense. #tag low overheads and genericity.
Okay, 100x better security, resistant to AI attacks. That's phenomenal. But usually, security like that comes at a steep price, right? Performance tanks, power consumption goes through the roof, the chip area explodes. These are critical factors, especially for those billions of IoT devices. What about the overheads for CDSA? Is this actually practical for companies to implement?
This is arguably one of the most significant and exciting aspects of the CDSA approach, and why it's potentially revolutionary.
Mhm.
It achieves this unprecedented level of security with remarkably low overheads.
Really? How low?
The actual fabricated test chip showed just 1.37x area overhead and 1.49x power overhead compared to the unprotected AES core.
So less than 50% increase in area and power.
Roughly, yes. And critically, there was no performance degradation. The crypto core ran at the same speed.
No performance hit at all.
None reported. Now, compare that to the 3x, 4x, or more overheads we discussed for some traditional countermeasures like WDDL, which offer far less security.
It's a completely different league.
It really is. For industries like IoT, where, as we've said, every milliwatt and every square millimeter counts, achieving this level of security with such modest overheads is a genuine game changer.
So we're seriously talking about a countermeasure that's potentially 100 times more secure than previous state-of-the-art solutions, resists advanced AI attacks, and does it with comparable or even lower overheads than those less effective methods.
Based on the results presented in this research, yes, that's the takeaway. It's not just a win for security, it's a massive win for practical industrial adoption. It suggests companies might not have to make that painful choice between strong physical security and meeting their cost, power, and performance targets.
That sounds incredibly promising. Is it tied only to AES, though, or can it protect other algorithms?
That's another fundamentally important point. CDSA is designed as a generic countermeasure,
Generic meaning.
meaning it's not tied to a specific crypto algorithm like AES. The CDSA hardware essentially wraps around the power supply of any digital core. So you could potentially wrap it around an ECC engine, a SHA-3 core, even a proprietary cryptographic block.
So you can protect existing crypto designs, preserve legacy implementations.
Potentially, yes. And it's also designed to be technology scalable, meaning the principles should apply as chip manufacturing moves to smaller process nodes in the future without needing a complete redesign from scratch each time.
Wow. So that combination, incredibly high security, remarkably low overheads, and being universally applicable or generic, that seems like the holy grail for side-channel defense.
It really does address the key limitations of previous approaches. It represents potentially a new era for digital security, tackling the problem right down at the fundamental hardware level, addressing the root cause of these insidious side-channel leaks instead of just patching over them. #tag future horizons and your provocative thoughts.
This has been a truly eye-opening deep dive. It's crystal clear that this whole field is a constant arms race, isn't it? The dance between attackers finding new vulnerabilities and defenders building better walls never seems to stop.
Absolutely. Each breakthrough on one side inevitably spurs innovation and new thinking on the other. It's a dynamic equilibrium.
So looking ahead, what does this all mean for the future of digital security? Where do things go from here?
Well, from the attacker's perspective, you can bet researchers are already thinking about how to push back. They're likely looking at ways to integrate the AI power of XDeep SCA with the physical automation of SCNIFR to try and make attacks even faster and more efficient.
Combining the brain and the brawn of the attack.
Exactly, and improving the ability of cross-device attacks to work even on the extremely low SNR EM traces that something like CDSA might still leave behind, however faint. The quest for more sensitive probes, better signal processing, smarter AI to find residual leakage, that will undoubtedly continue. The attacks will keep evolving.
Makes sense. And on the defense side, what's next for CDSA and this white box philosophy? How will these innovations continue to evolve to stay ahead?
There are several interesting directions. The paper mentions exploring fully digital implementations of CDSA. The current design has some analog components. A fully digital version could make it even easier for industry to integrate into their standard digital design flows, potentially reducing complexity and cost further.
Okay, making it even more accessible.
Right. Another really fascinating idea mentioned is proactive attack detection. Imagine a system that could somehow sense the presence of an EM probe nearby, or detect the characteristic patterns of a side-channel measurement attempt as it's happening.
Like a burglar alarm for side-channel attacks.
Kind of. And if it detects an imminent attack, only then would it engage the full CDSA countermeasure. The rest of the time, it could potentially run with lower protection to save power. This could offer an on-demand security posture, balancing energy efficiency for battery-powered devices with robust protection when it's actually needed.
Being smarter about when to deploy the defenses.
Exactly. It's about being smarter, not just stronger, in how we apply these countermeasures.
Yeah.
Hashtag tag your provocative thought.
This deep dive has really shown us something quite profound, I think. The future of keeping our digital lives secure isn't just about writing unbreakable software code or relying on abstract mathematical proofs. It's increasingly about understanding and controlling the actual physics of computation.
The nitty-gritty physical reality of how chips work.
Yeah, the subtle energy they emit, the patterns of electrical current flow, the faint electromagnetic fields they generate. It's about designing chips that don't just compute accurately, but also manage to keep their operational secrets quiet while they're doing it.
Designing for silence, in a way.
Exactly. And this brings us to a final, maybe provocative question for everyone listening. As our lives become ever more deeply interwoven with these smart, connected devices in our homes, our cars, our cities, our critical infrastructure, and as these physical attacks inevitably become more sophisticated, more automated, more AI-driven,
Will the ingenuity of defenders, using this white box, physics-based security design, always manage to stay one step ahead of the ever-improving sniffing capabilities of the AI-powered attackers? Is it a race we can keep winning?
and maybe think about this too. What other aspect of our complex digital world beyond just crypto keys could you imagine leaking sensitive information through some subtle, unexpected physical side channel next? And how might we start thinking now about defending against it long before that specific threat becomes widely known or exploited? Hashtag Tad Channel outro.
And that wraps up our deep dive for today. We've journeyed from understanding the fundamental, almost invisible threat of side-channel leakage.
All the way through to the advanced AI-powered attacks like XDeep SCA and the automated physical reconnaissance of SCNIFR.
But critically, we've also landed on a potentially revolutionary defense in CDSA and Stellar, born from that white box thinking, offering unprecedented security with remarkably practical overheads.
Yeah.
It really feels like a path towards securing our digital foundations in a much more robust way. We certainly hope you've gained some valuable insights into these hidden vulnerabilities that exist right down at the silicon level of our digital world, and also into the cutting-edge engineering that's working tirelessly to secure it. It's a fascinating field where the tiniest physical details can hold the biggest secrets, and defending them requires truly understanding that physical reality.
Thank you so much for joining us on this exploration. Stay curious, stay informed, and we'll catch you on the next deep dive.